Okay, welcome everyone. My name is Simon. I'm going to tell you today how C++ debuggers work. This is my background, so you know kind of a bit where I'm coming from. So I worked at Codeplay here for about 5 years, and my first few projects were all working on debuggers. So I worked on debuggers for OpenCL and HSA. These are like heterogeneous programming models, so debuggers for GPUs and CPUs and any other things you happen to have in your system is the kind of idea. These were all based on LLVM's debugger, which is called LLDB. And I also worked a bit on the dwarf debug information format. Submitted a couple of proposals in there. So this is kind of where I'm coming from and how I learned what I know about debuggers. So first I want to talk about, so you have an idea of exactly what it is I'm going to tell you about in this talk. So does anyone know what this is? Yes. By whom? Grace Hopper, yes. First actual bug found in a machine by Grace Hopper. Does anyone know what machine it was? I can't remember either. But nowadays, our debuggers look maybe a little bit more like this. This is LLDB running in a terminal. Or like this, which is GDB running inside Emacs. Or maybe look like this, which is like a nice curses interface for LLDB. Or maybe you look more like this, which is just the Visual Studio debugger. Maybe I should plug this one more because I work for Microsoft now, but you know. Yay, Visual Studio. So debugger is an application which is used to test and debug other applications. So this is kind of maybe a broad term, can apply to other things. So a little bit more specifically, you want to do things like set breakpoints, step around your code, evaluate expressions. What is the value of this expression at this point in my code? Or view my backtrace. How did I actually get to this function which I'm in right now? In order to explain all these concepts, I'm going to be using a kind of specific platform. These concepts do broadly apply to other kinds of platforms, but just for simplicity, I'm going to stick to Linux with 64-bit x86 processor, using ELF as object file, Dwarf as debug information, and Ptrace as a debugging library. You don't need to know what all these terms mean yet because I'm going to be explaining them. So don't worry if some of this looks weird. As long as you know roughly what Linux and x86 are, we should be okay. Does anyone not know what Linux and x86 are? Okay, we're in the right place. So this is what ELF looks like. I don't expect you to be able to read all of this. I just put it up because this is really, really nice. If you look at the slides later or go to korkami.com, this is a really nice pictorial description of what ELF looks like. There's an even more detailed one which would look just tiny on a slide, but the basic idea is this is a file for storing objects. So your code sits in some file in your computer, and it's encoded in binary, and your operating system has loaders which understand this file format. They understand, where do I find the code? Where do I load it into my address space? How am I going to actually execute this executable? Or maybe it's a shared library, and it has other information with regards to that. So ELF is kind of a way of describing all of the different things you want to describe about your executable or shared library to the loader, so that you can actually execute these things and link them at runtime dynamically. Debug info, of course, is made up of lots of these things. Dies. But they don't look like that, they look like this. So this is a dwarf information entry. And what this essentially says, this is a compilation unit, which corresponds to essentially a file in C++ with all of the includes kind of shifted into it. So this tells you a little bit about the compilation unit. It tells you, I was produced by Clang with this version. I was written in my source language in C++. I came from this file. Here are the low and high PC addresses which I might be running at. So this kind of tells us broadly some high-level information about our executable and the source code which it came from. So dwarf is the means by which we go from our binary machine code, which has been loaded from our elf file, and link this somehow back to our source code, which we wrote in C++. Right, so our computer needs, our debugger needs a way to be able to say, okay, we've got a function in C++. Where's the code for this thing? How do I find it? And that's what dwarf and debug information do. On Windows, you have things like PDB, which do broadly the same thing. Dwarf also has line table information. So just as well as knowing like which compilation unit does this come from, I might say, okay, if I am at this program counter, then which line in my source code am I actually executing? And this is a means to map that back. So you can see it says that I came from variable.cpp, and these are a bunch of different lines in my source code and which program counters they relate back to. So actually this gives a fairly easy mapping between addresses we're executing in memory and source code sitting on our file system. So this lets us actually map these back to each other. Does this all make sense? Mostly not. Good. Ptrace is Linux's way of exposing kind of debugging operations to the user code. So in order to debug programs, you need access to things which the operating system is doing. You need to be able to like hook into processes which are running. You need to be able to stop them. You need to be able to read their memory, all of these things. And some of these things aren't things that normal user mode programs can just willingly do on any process running in their system. So what we need to do is we have syscalls to actually go into the operating system and do all the necessary machinery in order to give us our debugging experience. And that's kind of what Ptrace is doing. It has this wonderful, beautiful interface. It takes a request, a PID, and then some address and some data. And these may mean totally different things depending on what request you pass in. If you're ever designing an API, don't do it like this. But it's what we're stuck with. So some things you can do are, you can say, okay, I want to allow tracing to happen on this process. Or I want to read memory of some other process. I want to read registers, write registers. So these are all just enumerators which you pass in as a request. And then depending on what that request is, then the other arguments are interpreted differently. Yes?
Does this mean that if you compile with debug symbols, you'll be linked against debug library, Ptrace library implicitly by the compiler?
Sorry, can you say that again?
If you compile with debug symbols, does that mean the compiler is implicitly linking you to the Ptrace library?
So the question was, if you compile with debug symbols, are you getting linked against Ptrace? No, so Ptrace is something which you call into, which the debugger is going to be calling into. So the debugee does not need to do anything with Ptrace. It's all the debugger which is actually using this library. So if you want to know more about Ptrace, you can check the man pages, as always. So that's kind of the broad introduction to Linux, which I wanted to actually cover. And now we're going to go into some of the actual things you want to do in your debugger and how they actually work. So breakpoints are the kind of main one where people think that breakpoints are magic. Right, you say, okay, I want to set a breakpoint on this line of my code or this function, and then through some magical machinery, you actually get a breakpoint and your code stops and you can inspect what's going on. and you can continue, and you can step, and all this stuff. But breakpoints are kind of opaque because we don't really learn about them. But they're actually not so complicated. Broadly, they're split into two different categories: hardware breakpoints and software breakpoints. The differences between these are hardware breakpoints, you essentially have special registers, and you write values into these registers which will do some processor-specific thing. So hardware breakpoints are very, very architecture-specific. They work quite differently on different architectures. Software breakpoints mostly work the same on different architectures, just the details which are different. But essentially you modify the code which you're actually executing in order to introduce instructions which will actually cause a breakpoint to be triggered. I'll show you some examples of this later. But also the thing to note about hardware and software breakpoints is that hardware breakpoints are limited because you have physical registers, and you can't have an infinite number of registers on an actual machine, generally speaking. So they're limited in number, but they're quite powerful because at least on x86, you can write some address into this special register, and then you can set some flags and say, okay, well, I want the processor to hit a breakpoint if this address is read, or this address is written to or executed. So this lets you do like data watch points. You can say, okay, when this thing gets updated, I want to know about it. And that's quite powerful. Whereas with software breakpoints, you can only really break on execution. You can't, because you're just modifying code which you're running, you can't really just say, okay, when you read this address, trigger a breakpoint, because this is just an address to the processor. It's just reading some memory. It doesn't know what you're trying to do. But they are essentially unlimited. Of course, there are constraints there, but you can think of them as being unlimited. So I'm not going to talk about hardware breakpoints a whole lot, but on x86 at least, you have 4 registers which you can write addresses into, DR0, 1, 2, 3. And then you have a status register which you can query, and some control registers to tell the processor if you want to break on reading, writing, or executing. So it's not so complicated. This kind of stuff is all usually hidden from the user, but you can just, if you have the means, you can just write into these registers and do fun stuff with your processor. Okay, cool. The software breakpoints are the main thing that I want to talk about. So I'm going to run through a demonstration. If at any point you get lost, please put your hand up and let me know, because this is maybe the most important thing, because people will like knowing how breakpoints work, and they're not very well explained in a lot of places. So I want to try and get this across. Barney, yes?
Just back to the hardware ones.
Yes.
If I did write a program that wrote something into those addresses, what does that do? If I'm not debugging it, I just write some stuff into those addresses, into the registers. Does that have an effect? Just the program I'm running that it has an effect on?
If you're running a program and you're just randomly writing data into these registers,
The debugger does.
Yeah, I can't remember exactly how these things get set, but I'll find out and let you know.
Are they same for x86?
Yeah, for x86, 64. Yeah. So imagine we have some code. Okay, so on the right-hand side is the assembly, and on the left-hand side is the disassembled binary. So we want to set a breakpoint on this move instruction. Okay. What the debugger will do, it will take this first byte of the instruction, this 0x48, and it will save it off somewhere. So the debugger is going to remember that there was this 448 byte. So then it's going to write in a special value oxcc. And what this is it's the int3 instruction in x86. So I'll get to what this instruction does in a bit. But note, what we've done is we've taken the first byte of an instruction out of code we're executing in memory, and we've replaced it with this new one. So now, when we get to this point, instead of our original instruction being executed, it's now going to be this int3 thing. So as for what int3 actually does, is, well, when we execute this first instruction, fine, we push this register, then we get to here, and then we stop, because int3 triggers an interrupt. Is anyone not familiar with interrupts? Okay, great. So essentially, the operating system can register interrupt handlers, so when different specific things happen in the processor, those interrupt handlers will get called, and they can do some special thing before eventually handing the control back to the application. So what Linux does is it registers this do int3 instruction function. This is the actual code from the Linux kernel. You can see it's doing some things like has some debug stack information, and then interrupts enabling, disabling. But then the most important thing is this do trap call. So this is going to send a signal to the process. So these are like Unix signals. Maybe you're familiar with them. Like you can send a kill signal to something or an interrupt signal. This sends a sig trap. The debug to the process which is being debugged. Yep. So sig, yes.
Off-topic questions. Want to be closed then?
Yep, we can close window.
Get very chilly, so I'm having blood.
Cool.
Gets hot, just so.
So if we want to know what signals mean, then we can go to our handyman pages. And this tells us that sigtrap is a trace or breakpoint trap. So what's going to happen? I'll run through like a full example. So say we have here on the left the debugger, which is waiting for the user to do something like press a button or input a command. And on the right-hand side, we have the process we're debugging. So the debugging is currently stopped. So let's forget about that for now. So the debugger is waiting for input. Say we press the continue button or we type in the continue command. Okay. So the debugger is now running, and it's going to continue the debugging process. Then what it's going to do is wait to get a signal. So it's going to wait for a signal to be sent to the debugger. That's what wait PID is going to do. So now the debugger is running because we continued it, and the debugger is waiting for a signal to be sent to this process. Okay? All with me? Great.
So at the beginning, it's before we throw the int3, yeah?
Mm-hmm.
Yes,
the first
yes.
comment, there's a push, yeah?
Yep. So this is, we're currently at the push, so we haven't done an int3 yet. So now the debugger is running, and now we get to our int3 and we stop, and we transfer control over to this interrupt handler. This is the thing we saw before, but just cut down a little bit for space. And now this sends a signal, a sig trap. And now the debugger sees that there's a signal sent, so it gets woken up. It got signal, and now it can do whatever it wants. It can read registers to find out where the process was stopped. It can read memory. It can do anything. This is how breakpoints work. Any questions on this? Yes.
So that signal gets sent to all the processes that are listening to it, or to
That signal gets sent to this specific process. So that will be, I guess, encoded in some state.
How does it go to the debugger and not the debuggee?
It goes to the debugger. The debugger is waiting on the PID for the debugger process.
Okay, and what if I press M? In this
What if you press start?
GDB. So how can I recover the next command? Because it should be 48, 89.
Sorry, can you say?
Because the second command is not in 3, it was move. It's far as I remember. Yeah. So we should recover the second comment, yeah, somehow.
All right, yeah, we need to eventually actually run the code again. But just for what's gone on so far, are there any other questions? Yes.
Is int3 specifically an interrupt for debuggers?
Yeah. Yep. So there's so most interrupt instructions in x86 are not just 1 byte, because you have the interrupt opcode, and then you have operand for which interrupt you want to trigger. But int3 is special because you want it to be a single byte. Then there's a special instruction just for int3 so that debuggers can do this kind of trick. Yes.
How does so from the debugger, you would give the debugger the process ID for what you're debugging?
Yeah.
How does the debuggy get the process ID for the debugger? Does that?
It doesn't need
part
it.
of the int3? How does it know what to send?
So the debuggy doesn't know what to send back. It's all handled by the operating system. So the debugger essentially when it launches a program, before it actually starts executing the real program, it will issue like a trace me for Ptrace. And then when it forks, it gets the process ID for its child, and now it knows what's going on, and the operating system knows what's going on. So the debuggy doesn't need to know anything.
So it's kind of like the operating system kind of wraps the process that you're debugging.
Well, I mean, the operating system's already doing that anyway. It's kind of just hidden.
Does the same principle apply even if you have multiple instances of the debugger running? So
yeah, if you have multiple instances of a debugger running, I think you can't attach to the same program, because I think Ptrace will do nasty things.
Because it's a database of multiple debuggers trying to insert.
Yeah, I don't think it would go well.
You could
Yes.
put a CC with another CC.
Yeah, Alistair.
Probably Ptrace just return the error in case it is right to send the same command to the same process.
What's that, sorry?
Probably Ptrace just return to your error if you try to send trace start to the same PID.
Yeah, but there's also like attaching to processes which are already running as well, which requires like certain permissions in the kernel. But I don't want to get into that's like super Linux specific stuff.
It's a
But
bad scenario.
anyway, questions at the back.
Yeah, what would happen if your debuggy called Ptrace itself or DLC?
Yeah, if your debuggy calls Ptrace itself, I think that causes problems. Yeah. Alistair, do you have a question?
Basically, my question: what debuggy is a debugger?
Yeah. I mean, because I worked on debuggers, I spent a lot of my time debugging debuggers, and sometimes you did see weird behavior that you kind of learn to expect it. Okay, so before I get on source level breakpoints, I didn't have slides on how you actually end up running the original instruction, but I'll get to that now. So because obviously you originally had this move instruction, you presumably want to actually execute this. I mean, you didn't just put there for it to be pretty. So what you do is, remember we saved this off. So what we'll do is put it back, and then do a single step over this instruction, then take it away again, and then continue. Because it might be that this thing is in a loop, and we want to presumably keep hitting this breakpoint. So we don't want to just put the instruction back and then continue because we might miss the breakpoint. So we have to it's currently off, so we put it back on, we step, we take it off, and then we continue. Yes?
How did you actually do that single step?
I'll get to that in a bit. Yes?
That's because this might be getting a bit ahead. I assume like if you're stepping through the source, it would jump to the next line of the...
Yeah, I'll get to source level stepping in a bit as well. Yeah, I'll get to stepping later. Yeah, there are other things you can...
should return this error, and also you should decrease the command pointer, right?
Yeah, you need to... Because once the PC steps over this, you need to put it back. So you need to just decrement the PC before you do any of that. Okay. Source level breakpoints. So source level breakpoints, now that we know kind of how the low level machinery works and we have a vague understanding of what debug information is, this is actually fairly simple. So if we want to set a breakpoint on main, we go into debug information. We say, okay, where does main live? What address ranges consist of main? And so we can find this subprogram die, and oh look, this says the name is main. And oh look, it also tells us where it can be mapped in the virtual address space. So now we can just go and set a breakpoint on 0x400670. And it all just works like our previous example. So really the source level part is just taking our debug information, mapping that down to our machine code level, and then just doing everything we just did. Yes, Gordon.
Just wondering, what's the low PC and high PC?
Low PC is the, so if your code for your function and a big block, the low PC is the lowest address of it, the high PC is the end address. So it's essentially just the range that it's mapped at. Yes?
Sorry if this is a bit familiar. What does PC mean in this context?
Oh, program counter.
Thank you.
So one interesting thing is in C++, we have function overloading. So if we have a do thing which takes a double and a do thing which takes a string, maybe we want to just set a breakpoint at the double one, like this. So how do you think we would do that? Does anyone have any ideas? How could you tell these functions apart?
There's different names.
Well, they have a different name, but this name is not going to be in the debug information in exactly this form. Yes?
Use the mangle thing.
Yes, exactly. So,
Is that what I mean, actually? The different names.
yeah. So the names will be mangled differently. So in C++ doesn't specify how name mangling works, but essentially everyone uses Itanium apart from MSVC, which does something else. But so if you've never seen a mangled name before, this is what the Itanium ABI name mangling scheme looks like. Kind of have you can see the do thing kind of here, and then the D is the argument. So this is essentially encodes the signature in some way which is easily reproducible. Of course, because this is C++, the mangling for do thing for string looks like this. Not quite so nice, but you know.
So, sorry, the debugger knows this because it knows how the mangle scheme works? Or is
Yeah, so the debugger, most of the debuggers are like a GDB is kind of built with a lot of GCC machinery as well, and LDB knows a lot of LVM stuff, so it knows how the mangling scheme works. So if you say, oh, I want to set a breakpoint here, then it can just mangle the name, and then it knows what symbol to look for.
the compiler doesn't write the debug information as well?
The compiler doesn't write that name, but it will have the mangle name. The debugger knows how to mangle to get to the same thing. So the compiler and the debugger will match up. They'll both do the same steps to get the same symbol. Yep, so that's stored in your linkage name. So you can just look for the linkage name and then set a breakpoint, just like we already discussed. Line table information works very similar. Going to set a breakpoint at line 4. Okay, we look at our line table information. We see, okay, well, this is foo.cpp, and oh, look, here's line 4. These acronyms, you don't really need to understand them, but NS means new statement. So this is the, this entry is marks the new statement at line 4, and the program counter is 0x400686, so we can just set a breakpoint there, and we're off. Yes?
Does that mean that when you're stepping, it goes to the next statement rather than the next instruction?
When you're I'll get to stepping in statements versus instructions in a bit. In fact, I think that might be the next thing. Yes, Barney?
Are there 3 statements then for line 4?
Yes. Yeah, so that will be like...
character on the line or something?
Yeah, so it's all one line, so it will be something like maybe a function call, and its arguments are also function calls. So it'll generate presumably 3 call instructions, and the first one is the one we'd want to set breakpoint at. Stepping, yes, this was the next thing. Okay, so there's 4 main kinds of stepping. Instruction, stepping over a function call, stepping inside one, and stepping back out into whoever called you. It's also in Visual Studio step back. Marketing. So instruction step, if you're lucky enough, you might have a hardware single step. So you can just say, hey, Ptrace, do a single step. And Ptrace says, okay. And it does a single step over one instruction. Depending on your hardware and even sometimes your kernel version, you might not have this, but it's handy for when you do. I will explain what you have to do if you don't have this in a bit. If you want to step out, then this is reasonably simple as well. We work out what the return address is, and we set a breakpoint there. So I will get to how we do like stack unwinding later, but essentially there are ways to work out the return address. You work it out and then you set a breakpoint there. Yes?
Would the return instruction, would that be stored in the dwarf information at all?
So I don't think the return instruction is stored in the dwarf, but there are ways to get return addresses, which I will look at later.
Oh yeah, you just look at the stack.
Yeah. So if you want to step in, well then you can set a breakpoint at the return address, just in case you're actually at the end of your function and you need to return. And then you set a breakpoint at the next instruction in this function or callee. Does that sound simple? It's not simple. This thing takes a lot of engineering effort to get right. How do you work out what the next instruction is? Well, maybe it's just maybe I'm just going to go down to the next instruction. That's going to be easy. But what if I don't? What if I have a function call? What if I have a branch somewhere over there? What if I have a conditional branch and I don't know where I'm going? It's non-trivial to work out where you might be going. So what essentially you have to do is look at the current instruction, say, okay, where are the possible places this function is going to go? Or maybe by looking at the program state, I can work out exactly where this is going to go. And then you can set a breakpoint there. So sometimes you'll end up just setting like multiple breakpoints because you don't know exactly where something's going to end up jumping to. Yes, go on.
Do any debuggers ever generate a DAG of the call stack as it goes along, so it can just step back?
Do any debuggers generate a DAG of the call stack? I'm not sure. LDB ships an entire instruction emulator for doing this stuff. So that's definitely one approach. Generating a DAG of the call stack wouldn't help you the first time round because you don't know where you could end up, and it wouldn't help you if you jumped to a different place. If you were at some instruction, you jumped one place, and then the next time you got to the instruction, you jumped another place. Unless you actually examined all of those, you wouldn't be able to build that DAG.
There's also go-to exists as well.
Yeah, also go-tos. And well, I mean, it's all eventually going to map down to the same things at the machine code level anyway. But
the instruction emulator actually take a look at the out-of-order behavior of the processor and everything.
pardon, what was that?
The out-of-order execution that's built into the processors now. You have one line of assembly, and it's not just the branches. It's like the processor will do something weird as well.
Yeah, I don't know how it interacts with out-of-order execution. I suspect it's very conservative, as if it sees that a bunch of weird things could happen, it would just set a breakpoint everywhere, and then you're going to hit it, right? Probably. Yeah, so essentially you have to inspect code to work out branch targets. And then for step over, you do very similar things. You set in breakpoints of the return address and next instruction in just this function. So you don't want to go into other functions. This is all quite simplified because in reality you have like multiple breakpoints all going at the same time, and the debuggers will have like they usually call them thread plans, which will kind of say, okay, is this a breakpoint which I know about? Should I be presenting this to the user? You also need to think about C++ exceptions being thrown like in the middle of executing things. So this is all quite simplified, but it's the basic idea, yes.
So I was wondering, because in a step in and step over, you have the return address.
Yep.
Why do you need the return address?
You need the return address in case, like, if you're at the end of the function and you step over, you have to have something to do. So debuggers will usually just go back out to the last function, to the callee. So where it's going to return to, you don't want to just say step over and then just fall off into nothingness. Okay, so registers in memory. Does this answer the questions we had earlier about stepping as well? Yes, cool. Registers in memory. So reading registers is actually a lot easier than you might think. Essentially, you have this like user reg struct in Linux, and you just pass this to Ptrace, and you say, okay, get me the registers, and it gets you the registers, and something like this. So it's just a big structure of all the values of different registers, and you have all the names available, so you can read them. If you want to get like sub-registers in x86, you have to do some like bit jiggery pokery, but it's reasonably simple. So this is actually quite easy. You just call a function, you get the registers. And then if you want to actually change a register, then you just say I want to change my program counter as RIP, the instruction pointer. I just write 42 in there because, of course, 42. And then I just call setRegs. And this will set the instruction pointer to OX42. And so this is how, like you mentioned earlier, you want to decrement the program counter after you hit a breakpoint. This is how you do it. You just work out where you currently are, you decrement it, you write it back in. If you want to read and write memory, you can also do this fairly simply. You can call peak data, you can OR it with 1 to set the first bit, and then write it back in. Can anyone see any issues with this? Like if I'm wanting to set like a large region of memory?
There's a race condition there
Race condition?
between reading and writing.
How do you mean?
You read in the first line, then you OR with 1. Can not somebody else not have changed it by then?
You kind of assume that you're the only one doing this. If you're not the only one doing this stuff, then you're kind of screwed. But yeah, I mean, like if you have multiple things doing this, then you could build synchronization mechanisms on top. Is there another hand as well?
How do you know the size of the
How
How do you know the size of the piece of memory you're getting?
So, yeah, that is a good question, and it's exactly a word every single time. So you call peak data, and on 64-bit x86, you will get back 64 bits. And if you call poke data, then you're writing 64 bits. So if you want to set a megabyte, you're going to be making a lot of syscalls. And every single one of these has to make a round trip through to kernel mode and all the way back again. So this becomes super, super expensive. So later versions of Linux kernels, I can't remember what version, like not super modern, but after some point they shipped this process VM read V. There's a write V as well. Essentially, you have to supply more arguments, but it's mostly giving you the power you expect. You can say how much you want to write and where you're getting the data from. And then you can just read and write large sections of memory without having to do a ton of round trips into kernel mode.
is that part of the Ptrace library as well? Or?
No, it's not part of Ptrace, but it's these are syscalls as well, or getting down into syscalls eventually. So it's part of your. These are provided by your operating system. So it's not in the same header as Ptrace, but it's in like, I know, sys/something in Linux. Stack unwinding. So we mentioned. Sorry.
So, but what was the problem with int and pop?
With what, sorry?
Now you mentioned that it could cause a problem reading and writing to assembly. What was the problem?
The problem is it's super slow.
That's it.
So if you want to do this with large parts of data, like it.
Each time you actually call the syscall, so of course, yeah.
Yep. Stack unwinding. So this is what a stack might look like on x86 64. So all of the arguments which we pass, which we have been passed, go at the top here. We have the return address, the pointer to the last stack frame, so our caller's stack frame, and then we have any local variables. So if we declare int a inside our function, this is going to go here. If we have int a as a parameter, that's going to go here. This makes sense?
What is EVP?
EVP is the base pointer. It's like the frame pointer.
SP is the stack pointer?
SP is stack pointer. So say we have code which looks like this. We have Baz, which calls bar, which calls foo, and foo says hi. So if we want to set a breakpoint on this this inner call, and now we hit this breakpoint, presumably we want to know how we got here, because maybe this isn't the only call to foo here in bar. Maybe there's calls to foo all over our library, and we want to know where we actually got here from. So what we can do is, well, we can look at this frame, the saved frame pointer, and that will tell us where the stack frame for our caller was. So now we have some stack frame. We don't know which function it's for, but maybe we can work it out, because we also have our return address. And the return address is going to be within some region of code, right? Or we're returning back to some code, presumably. And with that, we can look up between our low PC and our high PC and see that our return address is going to be inside bar. So now we know that from our saved base pointer, we got a stack frame, and from our return address, we got a name. And then to go further back up, we can say, okay, well, what's the last frame? So we walk back along the frame pointer and back along the return address, and we work out we're at Baz. And we just keep on doing this. With the sys5 ABI, we can keep doing this until eventually the frame pointer is going to be 0, and that's when we know we can stop. No, I forgot I actually have a slide there. Any questions about this? Yes.
It's inlining screws this up.
Yes. Inlining most definitely screws this up. And dwarf information has dies for expressing inlining. So if you're in a function, you might not necessarily be in that function. You might be in a function which was inlined from somewhere else. So essentially, debuggers have to keep these large data structures so you know, okay, well, if I'm at this PC, it's within this range for this function, but actually it was inlined from this other thing. So they need to do a lot of work to keep track of that. Yes?
Just wondering, do you know if there's ever been any debuggers that have handled macros gracefully?
Any debuggers which handle macros gracefully? I can't really imagine how you would do that without doing additional source code analysis. You'd essentially have to parse the source code again with the same command line arguments, and then extract information from those macros, which would be a lot of work. So yeah, it would be doable, but I don't know if any debuggers do that, and I can imagine it would be expensive. Yeah.
How difficult is it to search through all this dwarf information? Are the debuggers normally quite smart at knowing where to find these address ranges?
Yeah, so essentially, I mean, so the debug information is very much a description format. It's not a lookup format. So debuggers will parse all of the dwarf information. It's packed quite densely, and then they'll from that information they'll build up a series of data structures which are optimized for doing lookups like this. Because the naive approach is just to read through the dwarf information to look for what you're doing, but that would be super, super slow. So you get very fast optimized data structures for doing all this lookup. Expression evaluation. So this is quite cool. If you want to print an integer, we have a myInt inside your program somewhere, and you want to know the value of it. Well, this is reasonably easy because we know how to read memory, and we have debug information to tell us where variables live. So we can look for variables with the name myInt, and we can see, okay, well, this lives at an offset of -8 from my frame, in my stack frame. So there are a few different ways that the stack frame can be expressed. It could just be in a register. Compilers like to not do this anymore because, hey, free register. So it could be in the call frame information, which is used for exception handling and stack unwinding for like C++ exceptions. Or it could be like, I don't expect you to read this, but it's essentially a series of ranges. It's like between these program counters, it lives here, and then between these, it was put on the stack, and then here it was put back in a register, and things like that. So this kind of tells you where things live. If you want to print out like myInt times a, it's a little bit more difficult. Still not entirely complex. What we could do is generate some like intermediate representation. This is LLVM IR. This is actually what LLDB does. Generates some IR code around this, and then it can actually. Oh, sorry. This is the C code which it generates, and then it generates this LLVM IR from that C code. And then it can just tell LLVM to interpret this, because we can get the memory for all of these variables. We just need to know how to actually multiply this. So LLVM can just interpret this IR and get us our result. If we want to do something a bit more complicated, like call a function, maybe this function has side effects. Maybe it writes into memory. Maybe it prints something out. So we can't just pretend to call this function. We need to do a bit more work. So we can do very much the same thing, compile to IR, but then we're going to lower to machine code. Sorry, that's just a JIT compile. But it's going to JIT compile the IR to machine code, and then that's going to get mapped into the address space of the debug process. All right, so now we've got a function, we've compiled it, we've taken the actual machine code, and we've dumped it into the program which is currently running. Then we execute that function by changing the program counter and continuing. So we are actually really calling this function. We're just actually compiling something while the program stopped, then just inserting that function, running it, and then we're gonna, at the bottom of it, we'll just write some code to set all the state back, or we can do that with Ptrace, depending on what state. Yes, Alistair?
I don't understand where it gets source from to compile.
The source is generated by the debugger.
Oh, okay.
So this is C source, well, C++ source, which LLDB generates from the expression which you give it.
Right, so the expression will call the function.
Yep. So it's essentially like in here, instead of my int a, it would call foo, and then in the IR that would show up as a LVM IR call instruction, and then that would get lowered to the machine code instruction to call that. Does that all make sense? Yes.
Doesn't it already have a compiled version of foo?
It has a compiled version of foo, but it doesn't have a compiled version of something which will call foo and give me back my argument, my return value in a place which I can then know. Like maybe I can like find a call to foo.
Yeah.
That was my question.
Yeah.
The effects of that function are irreversible, right?
Pardon?
The effects of that function are irreversible. It changes the address space.
Yeah, I mean we could yeah, generally this will actually, presumably we're doing this for its side effects. If we were we might have a reversible debugger which would take a snapshot or something before that and then put the state back. There are a bunch of ways you can deal with that. If you want to do something like print myvec 5, then maybe you don't get this. Has anyone seen something like this before when debugging C++? Like if you have a std vector and you try and get the fifth element, like it seems it should work, right? But it doesn't. You get something like this. And this is because of the way that C++ templates work. This stuff eventually gets inlined away, and you don't actually have a function you can call. So one handy tip, if you're ever trying to do something like this with functions which are inlined everywhere, and you're getting errors like this, you could put something like this somewhere in your code. This explicitly instantiates std vector for int, and that will actually generate all the code for std vector int, stick that somewhere in a translation unit, and now you actually have somewhere where you can, where your debugger can jump to. This actually works. It's quite nice. It's super horrible, but I kind of love it. Okay, multi-threaded applications. As you might imagine, debugging multi-threaded applications can be quite difficult, but Ptrace has some handy stuff. So when you call, when you actually call a function to create a new thread, it's eventually going to call the clone syscall. And Ptrace has an option which you can set to say, okay, when clone is called, I want to know about it. So now whenever clone gets called, I get a sig trap. And I can actually get some more information about the sig trap and say, okay, well, was this from a clone event? Was this from a user breakpoint? Was this from something else? And then I can do whatever I want with that. So this is, I won't go into multi-threaded debugging much at all, but this is kind of the underlying machinery which lets you actually trace, okay, well, a new thread is running. Okay, now I have its PID. So now I can set breakpoints in it and get breakpoints from it and read memory in that address space and whatnot. So this kind of gives you the bare bones of what you need to actually support multi-threaded debugging. Yes.
Does this happen every time you make a new thread in your debugging?
Yeah, every time a new thread is created, this will get called. For shared libraries, so this is something which I struggled with for a really long time. I never understood how tracing of shared libraries worked, but it's super important because, like, if my executable is really just like a really small thing which calls into a bunch of libraries which are dynamically linked, I want to set a breakpoint on those libraries. And I might want to do it before I've even launched my application. But that doesn't really work because if I want to set a breakpoint in some executable before I've launched it, it's okay because I still have the executable, I have the dwarf information, I have the everything I need to actually know where I'm setting a breakpoint before the code is actually run. So there's a bunch of stuff you can do there, but for shared libraries, like if I want to set breakpoint before I even run my application, I don't even know what shared libraries it's going to get. So I need some way to actually get notified when some shared library is loaded. I want to know about it. I want to know where it's loaded so I can then go and set my breakpoints. Make sense? So there's this cool thing. This is sitting in the address space of your programs. It's just essentially a large, well, not very large, but a structure of a tag and some value, either a value or a pointer. And this just gives you some dynamic information about your program. So this lives in your program's address space somewhere. Now, one of these entries is going to point to something like this. So this is what's called a rendezvous structure. So this has some versioning information, and then a map to all of the shared libraries which have been loaded into this program. So that's all well and good. Like we can walk over this map to find the names and load addresses of everything, but it doesn't help us actually trace anything. So this thing, our break, this is kind of magic. So this, it's a function. Well, no, it's the address of a function, which is going to get called every time there's a change to what shared libraries are loaded. Okay, I'll say that again. So whenever you load or unload a shared library, the function which this points to is going to get called. So we can set a breakpoint on it. So now, whenever a shared library gets loaded or unloaded, then we get a breakpoint, and the debugger can walk over this link map and work out the names and load addresses of all our shared libraries. And this can happen every time something's loaded or unloaded. And it works really nicely. It took me ages to find this until it's like there's some header somewhere in GCC which just explains all of this, and it's great. So that's how shared library tracing works. It's pretty cool. I actually have a very simple implementation of this, which you can read to see what this is doing. I don't think I have a link, but I can show you later if you like. So remote debugging. This is what remote debugging kind of looks like. Like if you're sitting on your machine and maybe you're doing some embedded development, or you want SSH into someone else's machine and help them out or something. You've got your debugger sitting in your host, and then your target machine has some debug stub, it's usually called. In theory, this is just a very, very small wrapper over your operating system's debug library, like Ptrace. So the idea is the debugger is just going to be sending commands over, and the debugger stub's going to give you the answer. In reality, this thing gets huge. Like LLDB's debug stub has an entire instruction emulator. So, yeah. And then you have the actual program you're going to be debugging. So the debugger and the debug stub are communicating. The debug stub is using some OS-specific thing like Ptrace to communicate with the debugee.
Is the debug stub, is that a separate program, or is it something that's mapped into the memory of the debugee?
The debug stub usually will launch the debugee, so the debugee will usually be sitting in the same process as the debug stub. A lot of the time, it actually looks like this. So usually if you're doing local debugging, it looks exactly the same. It's just the host happens to be the same as the target. So if you use GDB, I think, at least LLDB, I think GDB does as well, operates exactly the same in remote mode as host mode. So it still launches this debug stub, and you do all the communication with the debugger. And this does not know anything about your debug information. All of this only handles addresses, essentially. And then so this arrow here The communication between the debugger and the debug stub is, for GDB and LLDB, it uses what's called the GDB remote protocol. And this is a protocol by which the debugger can communicate with the stub. It looks something like this. So I'm just going to split all of these out so I can explain them all. So there's just a $sign for the packet start. The Z0 is the type of packet. So like I want to read memory, I want to set a breakpoint, I want to do this, I want to do that. And then it has some arguments and then a checksum at the end to make sure that nothing got corrupted going over whatever you're going over. So for this specific example, this is the breakpoint packet, the Z0. This is the address to set the breakpoint on, and then 1 is some architecture specific thing. I can't remember what it is for x86. I think for ARM it's like whether you're running in ARM or thumb mode, so you know the size of the software interrupt address instruction, I think. But I can't remember exactly what it's for x86. Does anyone have any questions about remote debugging?
So any reason why this wouldn't just be any messaging format?
Oh yeah, I mean this could just be any messaging format. It's just that GDB had one, so LDB decided to use it because why not? And when I say it's like a common format, it's kind of not, because they all have their own packet types which only they understand, and they're implemented slightly differently, and they're all versioned weirdly. So it means you can't necessarily take like some nice new modern LLDB and then communicate with like some janky GDB server running on some embedded device from the early 2000s. It might work, but yeah, so this is just generally the format that people have stuck to. Any more questions? Because this is... Yes?
And the address that's sent in that, will that be corresponding to something on the target machine?
Yes. So this address is corresponding to the target machine. So the debugger has worked out where this address is living in the target machine, and now it's communicating with the target machine, with the stub, saying, I want you to set a breakpoint at this address in the debugging process.
So would the host have some sort of record of its own of the memory of the...
Yeah, so the host will know the load addresses, and it has all of the debug information and things like that, so it can do all the necessary translations. Yeah. Yes?
How is it possible to protect your application from like what is the idea behind it?
How is it possible to protect your application from something like this, or do you mean debugging in general?
That, for example, if you write some application, some person tried to debug it, but your application won't allow to do it.
Yeah, so for like if there's an application running, you'll only be allowed to debug it if you're I can't remember exactly what the setting is, but there's some kernel specific thing you have to do to grant permissions in order to be able to attach to any running process. As far as like writing your program such that someone who is running it on a system which they own can't effectively debug it, I mean, your compiler does a lot of that work for you just by optimizing. But I mean, people are always going to be able to do it. I mean, you look at any like reverse engineering stuff or like any game hacks or whatever, like no matter how complicated all of your work goes into to try and stop people understanding what's going on in your program, people are going to work it out. Yeah, I mean, I haven't worked on that kind of security area much, but yeah, there's a lot of people which do that stuff, and it's very, very hard. Okay, so that is how C++ debuggers work. Thank you. So I have some resources there. And how am I doing for time? Should I finish up? Questions?
Take a couple of questions.
Yeah. Any other questions?
ASLR.
Pardon?
Yeah, how does it work with ASLR?
Oh god, yeah. So address-based randomization. Essentially, what happens when you're running with address-based randomization is all of your executables actually look like shared libraries, which means that instead of just taking the addresses out of your dwarf information and using them directly, you need to work out the load address of the process, which you can get from you don't have to guess that, you can get that by asking nicely. And then you just offset that load address with everything. But you're right, ASLR makes it more difficult. Other questions?
You mentioned that we only had so many hardware breakpoints. The debuggers maybe hotspot those out in an hour.
Yeah, so the question was about having only a limited amount of hardware registers for debugging. Yeah, debuggers can, and I think do, swap them out. So if you, I can't remember if I ever actually looked at an implementation of this, but I'm told by people who worked on debuggers that there are a bunch of tricks you can do to make it look like you effectively have way more than you actually do, but I can't remember exactly how it works. But yeah, it would be some kind of like working out which ones are...
Next breakpoint.
Pardon?
Maybe you figure out a graph for the next breakpoint.
Yeah, you could work out like which one is possible to hit next, and then I mean when you're talking about like read breakpoints, it's more difficult because like nothing's really stopping just any random code from reading this location. Maybe you can do like analysis on the code and things like that. That gets complicated. Any other questions? Okay, thank you very much.